pandas and matplotlib for this project. I also need a train test split for this project. I also need metrics for this project, which I will import from sklearn.metrics. And I have to import ridge regression, lasso regression, and elastic net regression from sklearn.linear_model. So let's run this cell in order to import all these necessary Python libraries. Now I have to use the dataset regression_data. This dataset is present in my folder known as regression analysis. So I have to read this dataset from the folder. So we know that in order to read the dataset from the folder, we need to mount the drive and we need to set the path. So in order to save the time for this project, we have already mounted the drive and we have already set the path. So the path has been set, the drive has been mounted. Now it's time to read the data. So I have read the data and this is my data. We can see that it has 30 samples and it has only one feature which is known as independent data here. And it has a target variable which is known as dependent data in this data set. Now we can see the shape of the data. So the data has 30/2 shape. It has 30 samples and it has two columns. One column is for feature and other column is for target variables. Now I want to extract X and Y, that is feature and target variable from the data set. So let's run this cell. By running this cell, I have successfully extract the value of feature and target variable from the data set. And here is the shape of the feature. The shape of the feature is 30/1. It means we have only one feature with 30 samples. Now, this is a simple data which has only one feature. Now, in order to evaluate or in order to check the performance of ridge regularization, lasso regularization, or elastic net regularization, I need to make this dataset more challenging. So in order to make this dataset more challenging, it's time to add more feature to this dataset. This is also known as the feature engineering. So we are going to perform a feature engineering on this dataset by adding more features. So where to get the more features? So in the project of polynomial regression, we have learned how to find the polynomial feature. So we are doing the same here. Like I am finding the polynomial features and then I will transform this feature into the polynomial feature. So for polynomial feature, I am importing polynomial feature from sklearn.preprocessing. Then here I am instantiating the polynomial feature for degree is equals to 4. It means I am going to add three more features, that is x square, x raised to power 3, x cube, or x raised to power 4 in my feature matrix. So my feature matrix has shape only 30/1. So what happened after that, its shape will be 30/5 because the polynomial feature will also append 1 at the first column of the feature matrix, and then it will add 3 more degrees to the feature matrix. So here it is called a polyreg. After instantiating polynomial feature, I am calling this variable as a polyreg. Here I am fitting and transform my feature matrix into polynomial feature matrix. Let's run this cell. And now we can see this matrix. So we can see that we have 1, 2, 3, 4, 5 columns. Previously in our feature matrix, we had only one column. Now we have added 4 more features to make the feature matrix more challenging for the ridge regression, lasso regression, and elastic net regression. Now here we can check the shape of our polynomial feature-based matrix. So now the shape of our matrix is the feature matrix becomes 30/5. So this method is called feature engineering, in which we create new feature from the existing feature. There was existing feature X, we square it, we cube it, we take the power of 4 and we append them into the feature matrix. So that process is known as feature engineering, that is creating more feature from the existing feature. So here I am going to perform the train test split. This is my feature matrix now. This is my target variable. So these are the first two input to the function train_test_split. Now you have seen this function many times in this section now. So the test size is 0.2. It means I am using 20% of the data as it testing and remaining 80% as a training. So when I will run this cell, I will get 4 output. I will get the training component of our data, the testing component, the training labels, and the testing label. Now it's time to standardize the data. We know that in order to standardize the data, we need to import standard scalar from sklearn.preprocessing. Let's run this cell. So here I am instantiating the standard scalar. I am called the variable scalar. Here I am fitting this scalar to my training data, and here I am transforming my X data to the standardized form. Let's run these two cells. So the standardization of the data has been done. So the first time we are going to apply a ridge regression. Now for a ridge regression, I am using a function ridge, and I have already import ridge from sklearn. Here we can see that when we imported all the libraries, we have import ridge, lasso, and elasticnet from sklearn.linear model, and now it's time to apply ridge regularization. Now for ridge regularization, the first input I am giving, or the only input right now I am giving, is alpha is equals to 10. Now student, do not confuse this alpha. This alpha is a lambda. So basically in theory of ridge regression, we study about the lambda, that lambda is the parameter which controls the amount of ridge regression. So in Python, we do not use lambda. The standard stuff is that instead of lambda, we use alpha here. But in theory and in literature, since in literature, lambda is mostly used, that's why I use lambda when I was explaining ridge regression in the theory. But for Python, alpha is used. That's why I am using alpha here. So my alpha is equals to 10, which is the lambda parameter basically for a ridge regression. So here I am instantiating ridge, and I am calling this variable as a ridge. Here I am fitting my ridge regression to my training part. And here I am getting the intercept and the coefficients. So we can see that the first coefficient is 0. It means our first column of the feature matrix, or we can say that our first feature is not establishing any relationship with the output. If we go back and see, so we can see that our first basically column contains all the ones. So these ones are appended in our feature matrix due to polynomial feature function. So this one is not establishing any relationship with the target variable. That's why the coefficient or the weight associated with that one is 0. So this is our intercept, and these are the weights for remaining features. That is, this is weight for x, x square, x cube, and x raised to power 4. Now it's time to get the prediction for ridge regression from the testing component of the data. And here it's time to evaluate our ridge regularization. So we can see that ridge regularization has performed well, reasonably well. The value of R square is 0.82. The RMSE is 9562, and mean absolute error is 7090. So we have performed ridge regression on our data set. Now it's time to apply lasso regression. For lasso, I am instantiating the lasso function, and I am passing lambda is equals to 10. So I have already told you that the alpha for ridge and lasso is basically the lambda which we studied in the theory section of these two regressions. So the alpha is equals to 10. We also used alpha is equals to 10 for ridge, and here we are using alpha is equals to 10 for lasso. Let's run this cell. And now here I am going to fit this on my training and testing part, especially the training part. That is the training samples and the training label. So we are going to train our lasso regression model. So we can see that after training, we did not get error. But if you see here, we are observing the warning known as convergence warning. So let's see what this warning is saying. This warning is saying that objective did not converge. You might want to increase the number of iterations. So student, we need to increase the number of iterations in order to converge this model, or in order to fully train this model, or in order to get the optimal training for this model. Now here we did not pass any maximum iteration, which they are asking about, that you might to increase the number of iterations here. So let's see what are the other possible input to this lasso function. So we should remember that whenever we want to see a function which we are going to implement, like lasso, ridge, or any kind of function like train, underscore, test, or split, or any function which we have seen before, if we want to see the string document, if we want to see the document of that function, we can type help and lasso. So here I am going to type help and lasso to see what is meant by the iteration, which they are saying that you need to increase the number of iteration in order to get your objective converge. So when I run this cell, I can see this lasso function, and here I want to see the parameters which it needs. So if you see in a lasso, here is the important line to understand. The default value for alpha is equals to 1. That is, if you do not pass any input to this function, the default value of alpha, which is basically the lambda which we study in theory, is 1. Then fit intercept, it is true. That's why we are getting the value of intercept as well. And here is the most important thing. Here they are using maximum iteration of 1000. So basically we did not pass any max function here, but the default value is 1000. So what this warning is saying to us, that this value is not good enough. You have to increase your maximum iteration. Let's increase max iteration to 10,000 rather than 1,000. So here I have to pass one more input to this lasso function, which is max underscore it, that is maximum iteration. And right now I am passing the value 10,000. The reason is that the default value is 1,000. So this 1,000 is not enough in order to converge the training of the model. So let's pass the value equals to 10,000 here. So here I am passing the value 10,000. I put it into a comment. And now we have to train it again. Now, when I train it again, you can see there is no convergence warning. So we have solved the problem of a lasso function. The problem was the default value for the maximum iteration was 1,000, which wasn't enough to train this model on the given data set. So they were asking to increase the number of maximum iterations. So we increase the number of maximum iterations from 1,000 to 10,000, and we can see that now the model has converged. The warning error or the warning is removed. So student, it is highly advisable that whenever you want to see any function in Google Colab, you have to use help. Then you can write the function, then you can click and you can see the default values which are given to the function as an input parameter. And you can adjust accordingly if you want to change the default values. Like the default value of alpha was 1, but I want to use alpha is equals to 10. Therefore, I put alpha is equals to 10 here. Maximum iteration, I did not give any input for that. It was 1,000 as a default value, which wasn't enough to train the model. That's why they gave us the convergence warning. And now I changed it to 10,000. Now I did not get any warning. Now it's time to get the intercept and the coefficient. Now, this is a very interesting situation. We can see that we have two coefficients which are 0. In a theory of lasso regression, we learn that lasso regression try to simplify the model. It tries to give us the sparse model by putting the small value of the weights equals to 0. So this is 0. This was also 0 in the ridge regression. So that component is not playing an important part, or basically the first feature is not establishing any linear relationship with the target variable. If we see in a ridge regression, this weight is also small as compared to other weight. So what happened in ridge regression, we do not try to put the weights is equal to 0, or we do not want to remove the weights. But this value of weight is small as compared to other. Therefore, in a lasso regression has put a penalty on this weight and this weight. So basically on this weight, it put a penalty and put it equals to 0, and on the last weight, it is putting it equal to the negative value. Negative means this last weight has, or the last feature has, a negative correlation with the output variable. So we can see that here the model is simplified. One of the weight is more 0 as compared to the ridge. In ridge, we have only one coefficient equals to 0. Here we have two coefficient equals to 0. It means the model presented by lasso regression is a simplified model as compared to ridge regression. Now it's time to get the prediction from the lasso regression, and it's time to evaluate the performance. Now, if we see the performance of a lasso regression, its performance is far more better than the ridge on this particular data set. So the R2 value is 0.82 and here it is 0.9. So it is less than 7,000, the root mean square, and here it is more than 9,000. Similarly, if we compare mean absolute error for ridge, it was over 7,000, and for lasso, it is even less than 6,000. So for this particular data set, we have seen that lasso is performing better than the ridge regression. It do not only giving us the less amount of error, but also giving us the simplified model, which has even less coefficients as compared to the ridge regression. Now it's time to perform elastic net regularization. We know that elastic net regularization is the combination of ridge regression and lasso regression. So it has more input parameter. So here I am using elastic net. Here I am instantiating elastic net. The first parameter is an alpha. The other is L1 ratio. And here I am again using the maximum iteration of 10,000 in order to converge the training. So we know that from the theory, the L1 ratio is the most important parameter. It set up the contribution of ridge regression and lasso regression inside the elastic net regularization or regression. So basically, if L1 ratio is 1 here, it means the elastic net is basically the lasso regression, or there is no contribution of ridge. If I put L1 ratio is equals to 0.5, it means there will be a 50% contribution of a ridge and lasso. But if we go back, we can see that the performance of a lasso regression is far more better than the ridge regression in this particular data set. So first we try the L1 ratio is equals to 1 and see the result. So here I am getting the variable ENet. Here I am fitting on the training component of the data. Here I am getting the intercept value. Here I am getting the predictions. And here I am getting the evaluation metrics. So if we can see that these evaluation metrics for elastic net regularization are exactly the same as that of these evaluation metrics which were for lasso. The reason is basically here the elastic net regularization is working as a lasso regularization because we have L1 ratio is equals to 1. Let's set this L1 ratio is equals to 0.9. When I set L1 ratio is equals to 0.9, it means the combination of regularization is such that the lasso regularization is contributing 90% in the elastic net regularization and there is 10% ridge regularization. Let's run all this cell and see the performance of this regularization. Now we can see that the performance is getting worse when we include the contribution of a ridge regression. If we include the contribution of ridge regression more, that is now I am putting L1 ratio is equals to 0.5. In that case, there is 50% contribution of a ridge regression or ridge regularization and 50% contribution of a lasso regularization in my elastic net regularization. Let's see the effect of equal contribution on this particular data set. So we have run all the cell and we can see that the performance is getting worse and worse when we increase the contribution of the ridge regression. So we have seen that elastic net is the combination of lasso and ridge regression. So in this way, we have to select the value of L1 ratio carefully so that we can get the optimal result. So we can see that when we select the L1 ratio to the maximum value of 1, we are getting the best performance, that is the performance which is equal to the lasso regression. So if we run it again and we can compare it to the lasso regression again, so we can see that this performance is equal to the performance of lasso regression. So in this lecture, we learn how to implement ridge regularization, lasso regularization, and elastic net regularization in Python. We use a simple data set, then we make the data set more challenging by introducing the concept of a feature engineering. We add more features using the polynomial feature function, and then we made the data set more complex and more challenging for the ridge regularization, lasso regularization, and elastic net regularization. We call the process of adding more feature from the existing feature as a feature engineering. So after feature engineering, the size of our features becomes 30 by 5. So we had 5 features. We apply ridge regression. We applied lasso regression. We see that the performance of lasso regression was better than ridge regression. Furthermore, the lasso was providing a simplified a version of the model by putting a few of the coefficients or weight equals to 0. Then we learn how to implement elastic net regularization. So elastic net regularization is the combination of L1 and L2 regularization, or we can see that it is the combination of ridge regularization and lasso regularization. We see that the optimal performance is obtained when we put L1 ratio is equals to 1. That is when we remove the contribution of a ridge regression, and the whole contribution in elastic net was from lasso regression. So I hope you understood this project. Thanks for listening, and I will see you in the next lecture.